Welcome to chapter 2 of our linear algebra class and essentially a text of Go Book Strong. What he gets into now in chapter 2 is elimination and back substitution for 2.1. Title of this chapter is solving this equation, ax is equal to b, which is essentially why linear algebra exists. He puts in a very good conclusion notes to the end of chapter 1 that I would encourage you to take a look at. It helps describe his thinking. I've kind of alluded to it and I've mentioned it throughout some of the lessons. And that he's trying to introduce a lot of these big ideas early on, so then as we continue throughout the course, you can build on those big ideas and start wrestling with them now, because it's kind of been shown that interwoven spiraling idea is one of the best ways to teach, especially in mathematics, and constantly referring back to a single idea will help it stick more in terms of your long-term memory. Neuroscience. So in this chapter, we're primarily focusing on solving ax is equal to b. And when we're solving this, it's really important to note that we're going to be dealing with only square matrices. So we're talking about a square matrix A. This means instead of being m by n, we're sticking with n by n. This means that x, the vector that we're multiplying by or trying to solve for in the long run, is an n by 1 vector, essentially constructed of x1, x2, x3, all the way out to xn, where my final result, b, is another n by 1 vector, and we're trying to solve for b1, b2, b3, all the way out to bn. And so our purpose is focusing around this and essentially the results that can come out. In this, there could be no vector for x, like there's no x1 through xn, where we can multiply with our matrix A to get into B. Maybe there's only one singular vector that will solve this problem, or it's possible that there could be infinitely many. And hopefully that sounds very familiar. One of the nice things about linear algebra is that all of our equations are linear, so we're solving essentially a system of linear equations. That's algebra 2. And so even in the examples that I'm about to show for the 3 possibilities in solving this problem, you should quickly pick up on this because it's based off of algebra 2 and really building in that foundation. Where linear algebra can get difficult is when we expand the number of columns and equations that we're trying to solve, because it can get very hard to visualize what a 10th-dimensional plane looks like in an 11-dimension field. Even when we start talking about the third dimension in R3 and whether this creates a plane or a line is sometimes hard to visualize, especially in an intro course kind of like this is. And so in the text, and how we'll kind of start out is let's assume that n is equal to 2. And so if we were to kind of walk through some of the possibilities with n is equal to 2, just to kind of outline, and then we will look at kind of the simplest case of how we solve this, and that'll be the end of the first video, because I thought it would be a good breakdown to talk about the results for n is equal to 2, look at a third-dimensional problem, and then in the next video of this lesson, really start getting into, okay, well, how do we perform elimination? Where might elimination fall or fail, excuse me, and I think that would run together a little bit better. So you'll see that in terms of the construction. But if n is equal to 2, one of the possibilities is that we can get exactly one solution. So there's exactly one vector x that can solve my system, exactly one solution x. And in this scenario, what that means is that I have 2 independent columns if I can solve this. Independent columns. We saw in that last unit. That means the rank is a full rank. I have a rank of 2. In other words, I have 2 rows here because n is equal to 2 independent columns. So I have full rank because there's no dependent columns at all. But I have a rank of 2 in this scenario. One of the other things then that we can conclude from this is that A is invertible. Again, all of these ideas we're going to return to, meaning that A to the negative 1 exists. If you think about inverse notation when it comes to functions and how we undo functions, if I wanted to solve this problem, one way that we might try to solve it is by using inverse matrices, specifically inverse matrix multiplication. And knowing that if a matrix is invertible or not tells us if that's even possible. If I have a full rank, then I know that this must be true. And so as an example, with this, we also know, one more point, that if I was setting up ax is equal to 0, which we saw, the only solution to this is x is equal to 0. If there's more than one solution, then there are other vectors where this is equal to 0, not just the 0 vector itself. So all of these things we can conclude in this scenario. And so he gives an example. So here's a system. So 2x plus 3y is equal to 5. And then 4x plus 2y is equal to 6. If you take the coefficients here and form a coefficient matrix, 2, 4, 3, 2. This is my matrix A. Notice how it's a 2 by 2. My B is 5, 6. And we're trying to solve for x1 and x2 that if I was to multiply A by x would get me into that system. And there is a single solution here. We can kind of quickly see that if this was 1 and this was 1, then that would solve my system. And it is the only vector that would solve this system. So there's only one solution to this, and there are no other ones that work. I can tell again because these two columns are completely independent. This is not a multiple of this one, and so we have full rank. We have exactly one solution. The second case, or essentially what I was going to say too from algebra, was there's only one intersection point. If I was to graph these two lines, I would have one intersection point at 1, 1. We see that in terms of this point because one vector here outlines that in two-dimensional space. So that's one case. Same thing as if we were to go in to higher dimensions. The second way that we can have is if there are no solutions to ax is equal to b. In this case, that means that b is not a combination of any of the previous vectors. No matter if I have two independents or not, there's no way to get to b. B is not in the column space. So whatever the column space is, b is not in it. So b is not in the column space. Let's go ahead and use our notation CFA. So it doesn't matter what kind of combination, there's no way that we can get to that singular point, that my matrix A won't get us there. And one of the best ways to explain this, and you'll see this in terms of the system, is think about when you have n two-dimensional, n is equal to 2, so two lines. If I have two lines that are parallel, they will never intersect. There's no solution to that system, and that's what we're seeing here. So if I was to choose any point B that is not on those, even if it's on one of those lines, there's no way because it's going to work for one but not for the other, or not even touch anywhere else in the system. And so when we have a no solution scenario, imagine again that you're talking about two parallel lines. There's no intersection point at all. So that means the column space, every point that we could construct from that matrix, we wouldn't get that here. It would not work. So an example of that, something really similar to this one, if we have 2x plus 3y is equal to 6 this time, and then 4x plus 6y is equal to 15. If we try to solve this and set this up, so if I was to do my matrix, this would be 2, 4, 6. This would be 6, 15. When I go through and try to do, say, elimination, which is our process, like if I'm trying to solve the system, notice that by multiplying this equation by -2 and adding with the second equation, I essentially get that 0 is equal to 3. This would construct -12. And this is a false statement. Right? This, in terms of Algebra 2 or Algebra 1, even in solving systems, tells us that these two lines are parallel. There's no way they can intersect. There's no solution to this. And so I can't get anything from that. The last result that we can see, especially in a 2 by 2 case, is the case where we have infinitely many solutions. What that essentially is telling us is that we have dependent columns. We're not full rank. So we have dependent columns. It means that ax is equal to 0 for an x that is not 0. There is some other vector that I can multiply with a and get the 0 result. So there is some column that is ultimately dependent. And in the long run, when we're talking about a dimension of 2, if I have a scenario of infinitely many solutions or an infinite number of intersection points, that occurs when my 2 equations are the same line. And so it's a very similar setup to this problem, except if I change this so that the result came out to be 0 is equal to 0. If I was to do that, then these 2 are exactly the same line, and it doesn't matter what value of x and y I plug in, it'll always be true if we're on that line. Because of essentially the dependency. There are many ways to produce this. And so he'll get into, in terms of the text, there's a couple of things called free parameters and ways to set up and represent those solutions. We'll get more into that a little bit later. Although there is one set solution for B, like if you were to choose a point along that line, so for example, if 6, 12, 2, 3, 0, 2 would solve that system. Right, I could go in here and select 0, 2. If I choose any scalar of this, it would still set up the equation to be true in terms of adding that. So like 3, -2 would solve the 0 system. And so we get some free parameters there. And I know that's not super clear, but we'll break down into that a little bit more. Now, the last thing that I want to kind of hit on in terms of this video is, okay, we know the 3 scenarios, right? I can get exactly 1, we can get no solution, we can get infinitely many. The last thing, or really the next thing is, okay, well, how do I even get to this? How do I tell? What's the approach? And that's where the elimination idea from a 2x2 goes to a 3x3, to a 4x4, to a 5x5. And we start to extend this idea a little bit more heavy. And what it turns out that we can do is, as long as I manipulate both sides in the same manner, I can change my problem and rewrite it. And we saw this with the elementary row operations that I introduced to you at the end of the last unit. And we'll see that here as elementary matrices in terms of multiplication. Now, for us, what we're going to end up doing is transform our equation so that instead of dealing with a full 2x2 matrix, we want to transform it to be upper triangular. And when I transform it, we still have the same x vector. We're still solving for that original x1, x2, x3. But as I change A, we change B. Solving this system will solve the original system. And so the idea is, if I can take my problem and transform it into an easier problem to solve, then let's do that, because we can be more efficient and our solving practice will be a little bit better. And the way that we do that is through what's called backward substitution. The elimination piece, again, we'll hit in the following video. So let's say we've had a matrix A and we've gone ahead and transformed it into a matrix U. And that matrix U looks something like this. 2, 3, 4 across the top. 0, 5, 6, and then 0, 0, 7. We're looking for x1, x2, x3. And our solution to this is equal to 19, 17, and 14. And again, the takeaway from this right now is that this is the result of applying elimination matrices, going through and doing the elimination process to A to get to this. And why this is so important is that because these are non-zero numbers along this main diagonal, notice how I have the zeros underneath, thus this is called upper triangular. These boxes that I have are called pivots. And the fact that these are not 0 means that when I solve, we can solve for x1, x2, and x3 by dividing ultimately by these, but that the system is ultimately solvable. If I look at this last line, notice how it says that 7 times x to the x3, this is equal to 14. I can solve for x3. Because these are zeros, we're only now limited down to the single pivot. We can divide, and I find out that x3 is 2. Well, if I now go up a level, because I know what x3 is, the second equation now becomes a equation in one variable, and I can solve now for x2, because it reads as 5x2 plus 12, 2 times 6, so that's my x3, has to be equal to 17. Solving this, subtracting 12, dividing by 5, notice how we're dividing by that pivot, we get x2 is equal to 1. There's my second entry in terms of that x vector. Now I can go back to the first row, and I have 2 times x1 plus, well, again, I know x2 is 1, so that's 3. I have plus 4 times 2, or 8, and that's got to be equal to 19. And now I can solve this. 3 and 8 is 11, subtract it, divide by 2, I get x1 is equal to 4. And we've solved. End result, in terms of conclusion, is that the x vector that would solve this original system, we found by transforming into this new system with the upper triangular. And the fact that it's an upper triangular means we can use what's called backward substitution. It allows us now to solve it, and to solve it quite quickly, and we'll learn more efficient methods. But I now have my solution that x is 4, 1, 2. And in this, we essentially have one solution, and solving it, again, just notice that we had to divide essentially by those pivots. We always want numbers in my pivots that are not 0. You can kind of quickly see how this breaks down if one of these is a 0. If we have a 0 in the pivot position, we try to move that row, which we'll talk about. We create what's called permutations. Also, what we'll kind of start to learn and see is that if we're going to ultimately divide by 7, 5, and 2, we could go ahead and do that now. If my pivots are 1s, then that makes my solving way easier. There's no extra division. Whatever number I see is in the solution to this. And how we do this elimination, right? How do I get to this is going to be kind of the key part of this central section. And in the second video, we'll get into what that elimination looks like, and then what happens if this elimination fails. Now, one of the things that we can take away from this, again, that this has a singular solution, is that this means my matrix A has a full rank. So when my matrix has a full rank, that means all of my columns were linearly independent. And that means that in that case, I'll have a pivot in every column. I won't have any zeros along that main diagonal. We'll kind of see that impact as we go on. So 3 big things to take away from this first portion is that when I'm solving this system of equations, we can have exactly one solution like we did in this scenario. We can have infinitely many, or we can have none. How we find that is by transforming my matrix A into an upper triangular matrix U, where how I do that transformation applies to B, and in solving this new system, we're solving the original problem. In the next video, we'll talk about what that looks like.